This is a third topic, which is free energy and spontaneous. So the problem is the reaction is written and it is unbalanced. So I have to balance it out. And the temperature is 25 and 1 atmosphere pressure. So, okay, so this is given. And so I have to balance my equation first. Let's start with the lead. Lead is good. Nitrogen, 1 nitrogen, 2 nitrogen, I need 2 nitrogen. That makes it 6 hydrogen. Okay, so you need a 6 hydrogen here, make it 3 oxygens. Oh, you need 3 oxygens here, so then you make 3, and the 3 makes it 3. So you kind of goes around and comes around, and everything is what I call the self-consistent, and this is what you ended up writing it. So if I write it this is a 3, 2, 3, 1, 3. In a sense of the mu, this is the plus, plus, plus. That's a negative. Keep that in mind. Okay, so that's what I have figured it out. Okay. The second one. Second one, aluminum oxide. So you have a 2 aluminum. So you need a 2. That's done. Oxygen. Oh, you have 3 and 3 on each side. That's good. You have 2 ions. 2 ions. I guess that sums it too. So my constant is -1, -2, +1, and +2. And then I'm going to calculate my free energy. And here's a table, and I want to show you this one. Do you remember this, right? When you calculate the delta S, that's the table that I was given. Like I said, there is no delta here. Okay, there's nothing. It's just an entropy itself is given, and then once again, delta S naught is mu J S naught for each compound, and you just have to sum it up. In the case of here, right? This one, I want to know delta G for this particular reaction. Same thing, mu J, but here you have to do delta G formation for that compound. So I think that for this, I prefer to write the other way around. Formation for J compound, and you just have to do it tally up together. So that's why you see this difference between these two. Just a table, you just have to do the same tally up. And other thing that I did here is sometimes depending on the problem set, they have to give it to this value of delta G formation for each compound. For this pure state of element, they can give it to you, or they don't have to. And you just have to naturally know what's the value should be. And the value should be here. Right? It is 0 because of that's a energy, and the formation energy is you have to do it. So, and then okay. And I just have to write it one more time. So I will choose the same color now. So mu J here is lead +3, +1, +3, lead oxide -3, +2. You just multiply those numbers, and you just add them together. Luckily, those two, you don't even have to plug in your numbers because all 0. The only last 3 rows of numbers you calculate, and delta G for that reaction, which is what you just did, is each constant delta G formation of all the compounds. And what's the number here is -84.5 kilojoule. So once again, this is just that, not per mole, right? So what I said is essentially per reaction. Because this is an amount of energy change for particular way that the reaction is written. So to produce 3 moles of water, this amount of delta G is happening. So 1 moles of water formation, 1/3 of that value. So you can use that information in across the board, and that's why it was written in that way. Okay, second one, too. Like I said, aluminum pure, iron pure element, so it's all 0. And J is aluminum iron oxide. So is 2. Okay, so we multiply those numbers. Add them up. Delta G R for that reaction is delta G, as it is, whatever you call it, plus 835.4 kilojoule. I guess per reaction. Okay, so here's a case. One is negative. This is one is positive. These are the 2 contrasting examples. And when your delta G goes down, this is a spontaneous. This is not happening, right? So non-spontaneous. You should learn the scientific languages. Non-spontaneous. So that's not happening. And actually, if I go back, this is essentially not happening. If you put aluminum oxide, which is the white powder that is there, and if you put an iron and do all the part that you do thermodynamically, this is not going to happen. So that means, chemistry speaking, this reaction means that I want to reduce aluminum oxide into aluminum at the expenses of iron oxide into iron oxide. And that's what I want to do. And this thermodynamically, this is not permitted. So that's actually, once in the history of humankind, aluminum was as expensive as gold. You guys know that? It's actually Napoleon, his utensil was aluminum. And only the noble can use that because it's a light, shiny, and something hard to make, right? So that's why they used the aluminum was a precious metal was considered, although this is like a dirt, okay? It's so abundant. And now we are using it for a lot in the aluminum is used because we figured it out by using the electrochemistry, just using a lot of current. You can force this reduction, not using chemically, just electrochemically to reduce it into aluminum. And then once you have that, you can make aluminum foils and all kinds of things. Right? Car made out of aluminum, right? So this is actually one of the historically important curiosity. Can we reduce aluminum oxide into aluminum at the expenses of iron? We know how to convert from rust into something valuable, right? That's what we have an iron age long time before. We know how to do it. It's actually at the expenses of actually burning carbon. You know that, right? You put a lot of coals, and the carbon becomes CO2, and CO2 strip off from here to make this iron. We know how to make that, right? But from here, the other way is not. That's why the steel plant is such a CO2 factory. Okay? That's a problem. We cannot do anything about that.